welcome to today's class. Today we're going to start studying the upper half plane model of the hyperbolic plane. So recall that we defined the upper half plane to be the set of complex numbers that have positive imaginary part. So of course it would be nice to have a visualization of the correspondences between the hyperboloid, the unit disk, and the upper half plane. So let me do that for the disk and the upper half plane. So I'm going to do it here. So recall that the correspondence we have taken between the upper half plane and the disk is the Cayley transformation, right? So the Möbius transformation defined by this matrix, which it certainly sends infinity to 1, right? Because it's this divided by this is the image of infinity. It sends I to 0, right? Because here you know in the numerator you have z plus z minus I. And 0 to minus 1, right? Because it has to be minus I divided by I, right? So it sends U bijectively onto the disk, and it has this behavior on these 3 special points of the Riemann sphere, right? I mean, from these 3 special points, only this one belongs to the upper half plane, right? Okay. So it sends this here into this, and this ray into this segment, right? And actually, as one goes from 0 to infinity, from 0 to infinity, one goes from -1 to 1, right? So going from 0 to infinity corresponds to going from -1 to 1, left to right. Okay, now let's consider the stereographic projection. So we have the stereographic projection makes the upper half plane, which then I draw here, right? Because here I'm drawing this to be the x-axis. In this positive direction, and the y-axis in this direction. So the upper half plane would be this part, this part of the xy plane embedded in R3, and so on there the stereographic projection, the image is this open half sphere, right? So this part that lies here. So that would be the image, and of course the image of infinity, of course, it's this one. So this one will correspond to infinity, and then I corresponds to itself, and what else? And 0, 0 corresponds to this point. So this. Okay, so that's for the upper half plane, and then for the unit disk, so here we have the unit disk embedded in R3 in the xy plane, and so the stereographic projection takes it to it takes it to this open half sphere. Yeah, maybe let me draw it kind of. Yeah. And -1, 0, and 1. So -1 remains fixed by the projection. 0 goes to this one, right? And 1 remains fixed by the projection. So you see, so somehow the correspondence between the upper half plane and the unit disk becomes the relation between this open half sphere and this other open half sphere. Right? Now, exactly which relation? Well, in the half sphere that corresponds to the upper half plane, I go from 0 to infinity here, right? And in the sphere, in the half sphere corresponding to the unit disk, I go from -1 to 1 this way, right? So I think first you have to rotate along the x-axis, right? So let's say I take this half sphere and I rotate it 45 degrees along the x-axis. So after doing that, I obtain this sphere, right? And now infinity is here, right? And yeah, and then right, and so then I think one has to rotate this way, so to make infinity match, and then rotate again to make to put it on the other side. Okay, so in the end, the point is, in the end, the relation between the upper half plane and the unit disk becomes a certain rotation or certain composition of rotations, if you will, in the Riemann sphere. Okay, that is the Cayley transformation when interpreted as a function from the sphere to itself, and becomes a composition of rotations. Okay, we will come back later to these pictures. Later, I'm also going to draw the correspondence with M. But okay, so let's use the Cayley transformation to pull the hyperbolic Riemannian metric that we defined for D to U through the Cayley transformation. So don't forget that the Riemannian metric of the disk was itself obtained by pulling the Minkowski Riemannian metric of M through some other stereographic projection between D and M. Okay, so here's the formula. So given a point, and two tangent vectors U and V, tangent at Z, right? Tangent at Z. We define their inner product in that tangent space to be the inner product, and here I should say here I should have written as a subindex mu of 1 minus I 1I of Z, so at that point of the disk, right? And then what? Well, it has to be of the derivative applied to these points. Okay, now there are two things there's one thing to consider. We are using a very specific Möbius transformation, right? Namely the Cayley transformation, and of course there's the obvious question. Okay, so what if I decided to use another Möbius transformation to identify U with D? Right? Do I obtain the same? I mean, would this value be the same? And the answer is yes. And the reason will be that we are going to prove that the elements of PSL2R, so the Möbius transformations that preserve U bijectively, are Riemannian isometries of for this one. So if I use another identification, then you see, then I can go with Cayley transformation, and then go with the inverse of the other, and that will be a Riemannian isometry. So the Cayley transformation and the other one really give you the same. Okay. Okay. So on that side, there's actually not going to be no ambiguity. So if you would rather use another Möbius transformation that restricts to a bijection between U and D, you can just do it. Okay. And of course, there's then the obvious natural problem or natural question of finding an explicit formula for this one, right? Just like we did for the disk, right? That we defined it pulling the Riemannian metric from the hyperboloid, and then one of the first things we asked ourselves was what is to give an explicit formula, right? And we were fortunate enough that at any given point of D, the expression of the inner product at the tangent plane at that point was a non-zero scalar multiple, depending on the point, right? Depending on the point at which we take the tangent plane, but nevertheless a positive scalar multiple of the usual dot product, right? So, and that, for instance, that immediately told us that with respect to the new inner product, we can just measure angles in the same way as we do in the usually. So here we are again fortunate, and the same thing happens. The inner product at the point Z of two tangent vectors at Z, right, is this scalar multiple of the usual dot product between U and V, where again I am using the fact that since U is an open set of R2, this tangent plane is canonically identified with R2. And actually, this tangent plane also has, since it's canonically identified with R2, so it can actually be identified with the complex numbers, right? So here I could actually put complex numbers as, and the isomorphism being actually as complex vector spaces, right? Because here we can define multiplication by I. So whenever it's convenient, I'm going to think of this one as identified with the complex numbers, and just with the warning that then this one I'm defining it as a real inner product and not as a Hermitian product, right? I mean, here I'm not putting the conjugation, right? Okay. Right. I mean, here I'm not writing here minus. Okay. So the exercise is that you prove it. I would say it's again maybe slightly tedious, but very illustrative, I would say, this exercise. And then of course we would like to identify certain group of isometries, and maybe later on compute the whole isometry group for U with this Riemannian metric. And so the first step in that direction is that every Möbius transformation that preserves U bijectively, so every element of PSL2R, identifying PSL2R, with the corresponding group of Möbius transformations, with the corresponding subgroup of Möb plus C bar, which is the group of all Möbius transformations of C bar. identifying PSL to R with the subgroup of Möb plus C consisting of those Möbius transformations that preserve U bijectively. We have that every such Möbius transformation is an orientation preserving Riemannian isometry. So orientation preserving, well, you compute the derivative, right? And okay, and see that it's a positive, that it has positive determinant, of course. I mean, okay. Now let's prove it. Now recall this the polarization formula, which writes the inner product in terms of the norm. Now this is actually valid in any real vector space with inner product, and actually, and more generally, in any finite dimensional real space with a symmetric bilinear form. So since this one is symmetric and bilinear, it is valid. And this polarization formula, what it tells us is, in order to prove this, in order to prove that that nu is a Riemannian isometry, so that it preserves the dot product between any two vectors, it suffices to show that it preserves the norm, right? Because here, this one, the inner product between two possibly different vectors is written in terms of the norms, right? So that's what we do. So in other words, this polarization formula allows us to assume without loss of generality that U is equal to V. Okay, so let's prove that that GZU of V is equal to GZU of nu V, but here I mean I shouldn't be writing nu of V, and here I should write sorry. So let's say it's G of nu Z U, and then here the derivative, right, of nu at Z evaluated in V, comma, same thing. Okay, so first of all, yeah, so it suffices to show this, right? So, well, we know that our Möbius transformation is, is the Möbius transformation of some matrix in SL2R. Okay, and then we compute the derivative of nu at any Z in U in terms of A. So since here Z then is a complex number in particular, and the image of Z is also a complex number, so we can just compute the derivative in the usual way as in complex analysis, right? Without having to use the charts of C bar, right? Or without having to consider the chart that contains infinity, etc. Okay, so now the derivative then, as a linear map of between the tangent planes, is a multiplication by this complex number. So here you see it's we have this expression gamma z plus delta in the denominator, and in the numerator is alpha z plus beta, and the derivative is this one square, and then denominator times the derivative of the numerator minus numerator times the derivative of denominator, right? So this is the well-known rule, and then you see that gamma z alpha minus gamma z alpha cancels, and then we are left with delta alpha minus gamma beta, which is 1, because this matrix has the determinant 1. So this 1 is the determinant of A. So we obtain this. so the derivative is multiplication by this complex number. Okay, so that's the first thing. With the first ingredient we have to compute, right? And then we have to compute this square norm. Okay, so for that square norm, since you see that square norm is going to involve the image, the imaginary part of this base point, right? Of nu z. So somehow the next thing we want to do is to compare the imaginary part of nu of z with the imaginary part of z, order squares. Okay, so let's do that, right? And to do that, we write z as in the usual form, a plus bi. And then let's compute this quotient. So this quotient is of course this, right? And then on top we distribute, right? And we split into real part and imaginary part, the top. Okay, and now on the bottom, then what we are going to do is kind of to perform this quotient. We multiply by a 1, right? Namely, the gamma z plus delta conjugate, which then becomes just this, divided by that same thing. Okay, and then we have this is the this and this one are conjugate. So on the bottom we obtain simply the norm square of this one, and on top we write we write it using expanding z. Then we perform the multiplication of these two complex numbers. Okay, it looks kind of complicated, but you see here is the real part, and here is the imaginary part. Okay, now let's focus on the imaginary part. So here you see so alpha beta gamma alpha minus alpha beta gamma a. Let me say it once more. Alpha b gamma a minus alpha a gamma b. So this cancels, and then we are left with delta times gamma b minus beta times gamma b, right? Because I'm sorry. We are left with alpha b delta minus gamma b beta. B is a common factor, and the rest is alpha delta minus gamma beta, which is 1 because it's the determinant of the matrix, right? So all of this simplifies into simply b, right? B times I. Okay, so when we take the imaginary part of this, which is nu of z, we see that it's b, which is the imaginary part of z, right? Divided by this square norm. Okay, and now let's compute the square norm that we wanted. So the square norm is of course the inner product with itself. And here I should have written here it should be nu of z, of course, not z. Okay, and then this becomes well, since we are based in nu of z, we have to write 1 divided by the square of its imaginary part, right? I mean, here you have it, and that times the dot product of something with itself, which is interpreted, that itself, when we interpret it as complex number, it's just its norm, right? Or let's say as a vector in R2, let's say also, it's just the norm, right? The norm of what is inside here. But we saw that the derivative is multiplication by this number, right? Okay. right? So it's v times that number, and then it's the square norm, right? Because it's inner product with itself, so it's the square of the norm. Okay, so you see, okay, so here we have we substitute this imaginary part square with this one, right? So so on top, on the numerator, we're going to have the square of this one, so it's to the fourth, and then in the denominator we're going to have the image of z square, right? Because kind of here because of this square. Okay, so when so this is equal to this because of this equality. Okay, now square norm. So now now we interpret, let's say, this as complex numbers. So the norm of complex numbers opens the product. So this becomes this norm to the fourth, and then the square of the norm of v. And then we have this cancellation. Okay, and we are done, right? So because this is the square of the norm in this base point z. Right? Okay, and then the theorem follows by the polarization formula. Okay, so we have here already our subgroup of the group of all isometries, all Riemannian isometries that preserve the orientation. Later on, we are going to see that we actually have equality, which I would say is not a non-trivial theorem. But let's before going into proving the equality between PSL2R and iso plus of U, let us compute some hyperbolic lengths of some curves, and hopefully we would be able to classify all possible shortest curves in U. So let's take a kind of a very simple-minded curve, which is just a segment of the positive part of the imaginary axis, right? So we have these two positive real numbers, and then we take the curve that goes from AI to BI. So somehow the picture is that somehow AI is somewhere here, BI is somewhere here, and we are taking this segment parameterized in the most simple case, right, like linearly. Since we don't know the hyperbolic length yet, so we don't know whether this parametrization is by arc length or not, right? We are only doing the obvious thing. Okay, let's compute the hyperbolic length. So the hyperbolic length is by definition this integral, right? The integral of the norm of the tangent vectors, right, at all the points in the curve. Okay, now notice the derivative. Well, the derivative is of course I. Okay, and we are based at each point ti, right? Gamma of t is ti. So this inner product becomes simply this. Okay, and then it's just the integral of 1 over t, which is the logarithm, right? So the length of the curve is the logarithm of the quotient, right? Or the difference of the logarithms, if you want. Okay, so it was not so hard, and well, maybe we have actually found a shortest curve connecting A and B, right? So let's show it. So let take any curve of class C1, or if you will, piecewise of class C1. I mean, the same argument will work in that case. You know, and connecting AI to BI, right? Connecting to the same points we have already connected with this other curve gamma. Okay, and then let's compare the hyperbolic lengths of gamma and delta. So for that, it is convenient to write delta as its real and imaginary, in terms of its real and imaginary parts. Okay, so definition of the hyperbolic length is this integral, the integral of the norm of the velocity. When we compute, I mean, in the denominator we have to write 1. Well, I mean, in the denominator we have to write the imaginary part of the curve square, right? So, but the imaginary part is y of t. So this is why this appears here, and then the rest is kind of, it was the usual dot product of R2, right? So on top you have to write this. And then okay, then kind of just split it, right? I mean this write it this way in order to notice that you are adding something always to this number, right? So this integral becomes greater or equal than just having this, right? Because when you add the whole integrand can only increase, right? Okay, but then you see this starts looking already familiar, right? Because this square root will take the square root, so we know that y is positive because it's delta is a curve in U, right? So y is positive, and on top, well, that there you really have to take absolute value. Okay, but it's okay because the absolute value is always greater or equal than the number inside the absolute value sign. So we have this inequality of integrals, and for this one, well, we can already perform a change of variables, and well, the change of variables is you see it there, right? Okay, but this integral, well, we know it, right? It's the difference of the logarithms, and you see, and y of d and y of c are precisely a and b, right? Because delta of c is ai, sorry, and delta of d is bi, right? So delta, so you see y of c has to be a, and y of d has to be b, right? Okay, but this was precisely the length of our previous curve gamma, right? So this means that indeed gamma is a shortest curve, and notice if delta is not a reparametrization of gamma, then one of two things happens. Either you know, either the image of delta is equal to the image of gamma, but in that case somehow it has to have a vanishing derivative somewhere, or a point of discontinuity, and so on. But in that case, one really has to have its length greater, right? I mean, unless because if it's not a reparametrization, if it has the same image but it's not a reparametrization, that means that in going from ci to d, from ai to bi, it has to come back somewhere, right? Because otherwise it would be an injective reparametrization of gamma, right? Okay, but in that case, then as a parametrized curve, it's not a shortest curve, or the other possibility is if delta is not a reparametrization of gamma, the other possibility is that in going from AI to BI, at some point it leaves the imaginary axis, right? I mean, at least at some point, in which case there will be here some points that where this is actually strictly bigger than just this, right? So in that moment we are going to have, I mean, because of that we would have here strict inequality, which means that gamma is the only up to injective reparametrization is the only shortest curve connecting them, right? Connecting AI and BI. Okay. Okay. Now so this means that gamma is the only shortest curve connecting AI and BI up to injective reparametrization. Right? Okay. So when I say up to injective reparametrization, what I mean is up to up to an injective. Let's say up to a homeomorphism of the interval. Right? Okay, and then let's say up to a homeomorphism with non-vanishing derivative. Okay. Now the exercise is find a parametrization by arc length. So this is not hard. Knowing this is not hard. It's a good exercise, I would say. Very illustrative. It is possible. Okay. Now our next task, the next thing we are going to do is to pull this shortest curve gamma to shortest curves between arbitrary pairs of points. Using Möbius transformations, because now we know that Möbius transformations are Riemannian isometries, so they preserve arc length and they preserve the property of being shortest curve. Okay, so so somehow what we want to prove is that given any 2 points in the upper half plane, it is possible to send them to the positive part of the imaginary axis with some Möbius transformation, because then we know a shortest curve, and so when we undo, we obtain a shortest curve between the original points. So let's prove that for any 2 distinct points there is a Möbius transformation sending them to the positive part of the imaginary axis. I mean, we assume them different, right? Because otherwise it's obvious, I would say. I mean, if these are equal, then the result is obvious. Because actually, I mean, there obviously exists a Möbius transformation sending, let's say, W to I. Why do I say it's obvious? Well, because first of all, I mean, you see the picture is this one. So here is the positive part of the imaginary axis, and then you know, let's say that W is here. Then with a translation, I mean, with the translation, you know, the translation associated to the matrix 1 minus W 0 1. One moves W to the imaginary axis, to the positive part of the imaginary axis, and then how does one move then this to I? Well, just multiply with a positive real number, right? And multiplying with a positive real number is a Möbius transformation associated to a matrix of the form square root of the positive real number 1 over square root of the positive real number 0, 0, right, which is in SL2R, right? So even though the matrix itself, this one, maybe, I mean, is not, if lambda is different from 1, even when lambda is positive, this one is not in SL2R, But the corresponding Möbius transformation can be still represented by something in SL2R. Right? Okay, right? Or simply consider multiplication by a positive real number. It obviously preserves bijectively the upper half plane. Okay, so up to doing those two things, so up to translating and then multiplying with certain positive real number, we see that there exists a Möbius transformation, that preserves U bijectively and sends one of our numbers to I. Okay, so and the next thing is so at this point the picture, my picture is this one. Here is the positive part of the imaginary axis. I'm already located at the point I, right? This is nu1 of W, and then nu1 of Z is somewhere, right? I don't know, it's somewhere. And now I want to take another Möbius transformation that place it here, right? And maybe I try to fix I, so that I doesn't move and then this one goes to this, right? So it looks like what I want is some sort of rotation around I. Now these are more easily observed or located in the disk, right? Because in the disk is symmetric with respect to the rotations around zero, right? It's preserved by those rotations. So what I do is I go to the disk with the Cayley transformation, and that is why I wanted to locate this one at I, because I know that I is sent to 0 by the Cayley transformation. Right? Now the Cayley transformation sends infinity to 1, as we said before, I to 0, as I just said, and 0 to -1. Right? So somehow the picture is, here is the upper half plane, so infinity is somewhere, and then I have I and then 0, and these 3 points are sent to 1, 0, -1, right? And actually, if I go this way, I somehow go in this direction. But you see, I know that the image of the positive real axis, the positive real axis union infinity is a circle in C bar. So the image is a circle in C bar. So the image of the positive real, or of the positive imaginary axis has to be a segment of a circle, right? But these are collinear Euclideanly. So the image has to be this open interval -1, 1. Okay. Next. Which means that also the inverse of the Möbius of the Cayley transformation sends this open interval to the positive imaginary axis, right? The positive part of the imaginary axis. Okay, and now what I do then, then I see that what I want is, you see, I have here 0, which corresponds to nu1 of W. But I also have somewhere the image under the Cayley transformation of nu1 of Z is somewhere, right? And here it's quite easy, to just rotate and put that point here, which is where I want to put it, because I want the pre-image under the Cayley transformation to put it in the positive part of the imaginary axis. So that's what I do. This is my nu3. And then I go back with the inverse of the Cayley transformation, and it sends it sends W to I and the other point to the positive part of the imaginary axis. Okay, so good. So we are pretty much done. because now we can prove that the shortest curves in U are precisely, well, should they be? Well, if they give me two arbitrary points, well, I can send them to the positive part of the imaginary axis. Here I know that this segment is the shortest curve connecting these points, connecting this and this. And somehow I know how to characterize this one, right? The positive part of the imaginary axis, because what I can see immediately is that it's part of a circle in C bar orthogonal to R bar, right? So when I apply the inverse of when I go back from these points to these points, well, I know that the image of this one, has to be a semicircle in C bar orthogonal to R bar, because Möbius transformations are conformal, and so this segment, I know that then this corresponding segment is the shortest curve connecting these 2 points, the shortest curve. So I located I have found all the shortest curves, right? To describe them, all I need is to look at the circles in C bar that are orthogonal to R bar, and of course just intersect them with the upper half plane, right? Of course. So I obtain a family of semicircles, all of them orthogonal to R bar, and the shortest curves are all segments of these semicircles. Right? Okay. Okay, and then finally another exercise: find a parametrization of shortest curve of that shortest curve by arc length, right? Explicitly in terms of W and Z, right? So somehow you see one strategy could be to describe this new 1 and this new 3 here explicitly. So describe this explicitly, which can be described entirely in terms of matrices, right? I mean, this can be represented by a matrix which can be obtained by the multiplication of 4 matrices, right? So that can be done explicitly in terms of W and Z, right? So this can be done explicitly, and one can find the parametrization of this vertical curve gamma explicitly, right, by arc length, which is not this one, and then pull that parametrization by arc length here with this explicitly computed composition, right? So it is possible to do it, and the nice thing about that is that if one does it, then one can program it. Program it in terms, when they giving W and Z as the input and as the output, this parametrization by arc length. And something else one can do is, if once you have this parametrization by arc length, then maybe you can write a visualization program that actually lets you see the curve be traversed by arc length, right? So kind of by constant speed, constant rapidity equal to 1. Okay, so one consideration. So this theorem gives us an explicit formula for the inner product at any tangent plane, right, based at any point Z. And so you see, and it says somehow it's similar to what happened in the disk model, right? I mean, somehow we have here the x-axis, and what this says is, okay, if like if you take a point z, the dot product at two tangent vectors is the usual one but rescaled, and actually rescaled by a number that when the imaginary part is close to 0, this becomes the scaling factor becomes very big. So this means, so you see, so using this identification for every z, so that one can somehow take these tangent vectors and think that one can move them to other tangent planes. When we take those and we move close to the real axis, the dot product is kind of starts increasing and getting close to infinity, right? So in particular, if I take like a fixed vector and then I move z close to the real axis, the norm of this vector becomes bigger and bigger and bigger and bigger, right? So this means that somehow curves here that may look kind of very short to the Euclidean eye are actually very long, because their tangent vectors are, it is decided that the tangent vectors have very long norm, right? So somehow what the expectation one should have is that if I have 2 points kind of far away from the x-axis, they are actually going to be very close to each other hyperbolically, because somehow the shortest curve joining them is somehow really shorter than the shortest curve between points here. That is, points close to R bar are very far away from each other, and points far from R bar Euclideanly are very close to each other, right? So somehow things far away from R bar are small, and things close to R bar are large or very long, right? That's somehow the intuition. So let's see some animation. And let's see, where is it? Here. So you see here I can click on these 2 points, and what this draws is the shortest curve joining the 2 points, and it computes the hyperbolic distance between the points, which is the hyperbolic length of this shortest curve. So here the distance between these 2 points is actually 1.55, and so let's pick this one and get it close to R bar, and then you see how the hyperbolic length, it starts increasing a lot, right? And let's do the same here, right? So yeah, so you can see there, right? So I will have to zoom in to be able to get closer and closer to R bar. Okay, so all of this, so you see all of this is shortest curves. The reason why I can move this around and it kind of draw the shortest curve is because I programmed, right? I did these explicit computations that I mentioned throughout the class, and I programmed them. Okay, and now that is as far as it goes for the shortest curves, right? But let's see how parametrization by arc length looks like. Okay, so let's take a point here. One sec. Yeah, sorry, point to point. So I'm going to click on 2 points. The first one, the initial point, and the final point. I'm going to click in a second. And what is going to draw is the shortest curve joining them going from the first point to the second point with a constant rapidity. So you see, it looks like when things are kind of far away from R bar, it looks like it goes faster, right? And that when things are very close to R bar, the curve is traversed very slowly somehow. That has to do with the fact that somehow the segments that are close to R bar are actually hyperbolically very long. So it takes longer to traverse them, right? So it has to look like it's slower. Okay, so it looks like faster, right? And then let's see. Okay, now the other form of having a shortest curve is by as it happened, as we did in the hyperboloid model, right? I mean, to give the initial point and the initial vector and then traverse with that rapidity, right? So that's what I'm going to do. I click here, that's my initial point, and then once I click there, you see this thing here actually is the tangent plane at that point. So when I click somewhere, it gives me a tangent vector, and then it starts with that velocity, and then it maintains constant rapidity. But of course, it's not going to be like a Euclidean straight line. It has to be a segment of this circles orthogonal to R bar, right? So let's say here. Yeah, and of course I have to tell them to stop somewhere, right? Because otherwise it would never stop, right? It would well, we would have to prove that the length of the you see that if you have you see a full semicircle, right? I mean, in other words, take a circle in R bar orthogonal, take a circle in C bar orthogonal to R bar, a full circle, and intersect with a full circle orthogonal to R bar, and intersect with U, with the upper half plane. Then we have a kind of an open semicircle, right? And it can be seen that the length that this has infinite hyperbolic length. And that means, in particular, that if I start traversing, let's say, from a point here to either side, I will never reach R bar because the length is infinity. I think it's a good exercise that you try and do that. Of course, it's enough to show, for instance, that if you stand in the positive part of the imaginary axis, let's say you start at I, let's say, and then you start traversing in, let's say, vertically in the upper direction, that has infinite length, right? And for that you can just use this logarithm formula that we found, right? That the logarithm tends to infinity when x tends to infinity, for instance. So I actually already solved it for you. Okay, so I think that's it for today.